together. So I'll start off talking a little bit about gravity and water and explain this work that I've been doing with the NASA GRACE Gravity Recovery Climate Experiment mission and how it came to be, and why do we use gravity. And then talk a little bit about the satellites, and then focus in on some of the groundwater work, and then a little bit at the end about things we need to do, the communication we need to, we need to keep up that steady drumbeat while delivering the science at all different levels, to the general public all the way up to elected officials. Okay, so gravity and water. So why we're using a gravity satellite? So what's the connection? Well, first of all, we all know water is super heavy, and so it's so heavy that when it moves around the Earth, it does funny things to it. It changes its shape. It affects the spin of the Earth and the angle of rotation, all that stuff. And so these things are now measurable with great accuracy. And we can invert them to figure out the water changes, the water movement, the water storage changes that cause them. So, Earth rotation variations, length of day. So, the distribution of water on the Earth actually changes the length of day by very small fractions of a millisecond, but it's measurable. Polar motion is a big one that gets used a lot. The angle of rotation, how it wobbles, annual wobble, a Chandler wobble, which is a slightly longer frequency, and that's all measurable. We can trace out the path, we can look at how the angle changes. Here's a paper that came out, I don't know, maybe it was a year ago. So, the takeaway message was, hey, there's so much groundwater depletion that it's affecting the way the Earth rotates. And another one using polar motion and sea level rise to look at some changes in the global water cycle. Water is very heavy, and so it can deform the shape of the Earth. And this is an animation. Let's see if it actually works. Yeah, so on the left is the water load. So for example, you look at the Amazon, more water is in red. Here it's coming. So that's more water, and less water is in blue. And if you look over on this side, when there's more water here, when this turns red, this will turn blue, meaning the crust is sinking. So it's moving up and down in response to the load. So we can measure that. This was a piece of work that was done by my postdoc, Caroline Delianage. But Caroline did work with one of my graduate students, Carly Roulette, and used that impact of that effect of the weight of the water, in this case snow, and so correlated the crustal, basically the movement of the Sierras using GPS, and correlated that to snow water equivalent. And the one that we really want to focus on today is the static versus the time variable gravity and how we take advantage of that. So the static gravity field is the one that we know about, we learn about in textbooks, and so it's controlled by the position of the continents and the trenches and mountain ranges and the major topographic features of the Earth. But the time variable gravity field, and this is seasonal variations. The time variable gravity field changes in response just a little bit. So it's just a tweak to that static gravity field that changes, changing all the time, but we measure it now on a monthly basis. And that is primarily due to the movement of water over the Earth. So more mass in one place creates greater gravity, right? It's a greater gravitational tug, greater gravitational pull. And those minor variations are now measurable. And the way that we do it is with a NASA satellite called GRACE, which I'll talk about in just a minute. A lot of the geodesy and the potential of the geodesy, so geodesists are scientists that study the shape of the Earth, how it deforms, how it changes, and why. And hydrogeodesy is just sort of an emerging field that uses the geodetic measurements to understand what's happening. Okay, so let's talk about how we observe time variable gravity and terrestrial water storage from space with the NASA GRACE, Gravity Recovery and Climate Experiment, and GRACE follow-on. So GRACE was from 2002 to 2017, essentially wore out, and then the GRACE follow-on, or GRACE FO, was launched in 2018. So GRACE, Gravity Recovery Climate Experiment, the idea behind this. was to measure that time variable gravity with unprecedented accuracy and frequency, monthly, although there are weekly solutions. And the measurements would be used to really estimate changes in ice sheet mass, ocean mass changes, contribute to sea level rise, and honestly, the land stuff was just kind of an add-on. So, sort of like, by the way, maybe we could learn some things about water storage on land. And again, this all works because water is really heavy, and it's the heaviest thing that's moving on the time scales that the satellites are working. It's the heaviest thing that's moving around. So I like to say that the GRACE and follow-on function like a scale in the sky because they're perturbed as they orbit around. They're up at about 400 kilometers. They're separated by about 200 kilometers, and they're not very big. They're about 1 meter tall by 2 meters wide by 3 meters long. And as they orbit around, they follow each other around over the poles. And as they orbit around, if they encounter a place like the Sierras that's had a huge snowstorm, which hasn't, but we did, then it would have a slightly greater gravitational tug and pull the first satellite would come in and get pulled down a little bit, and then would pass and would relax back to its orbit, and the second one would come in and do the same thing. So it's almost like a scale in the sense it's moving up and down just a little bit. And the measurements of the position of the satellites are made with extreme precision, like thousandth of a sub-micrometer, a thousandth of a millimeter, better than that. So real accurate measurements of the position of the satellites and the position of the scale. So because we've got these great measurements of the scale moving up and down, as it orbits over the Earth, we're able to track the changes, not the absolute amount, in the total water storage, all of the snow and the surface water and the soil moisture and the groundwater together. If we want to pull out the groundwater, then we need other data on the snow and the surface water and the soil moisture to remove it from the GRACE signal. We work well at monthly timescales, and we're down to 25-kilometer resolution, but that is after what we call model-based downscaling. So it's really a product, it's a model, it's a GRACE and model product now that a lot of people are using, and it's 25 kilometers. It's produced by NASA. And the accuracy is 1.5 centimeters. Actually, the accuracy at this, we're at the 625 kilometers resolution is actually greater than 1.5 centimeters. So I have to figure that, recalculate that. But in short, it's a decent accuracy. It's not a hydrometeorology satellite. It's not going to tell us how much soil moisture is in downtown Albuquerque today. But it is going to tell us, if we look over a big chunk of the state, a big major basin, how the water storage is changing. I'll show you some of these. How the water storage is changing in, the upper Rio Grande or something on a monthly basis. And we'll take a look at some of that. That's the launch of the follow-up. It was a lot of fun to be there. Only satellite launch I've ever went to. This is Vandenberg Air Force Base, so really, really exciting to be there. One of the major products of the mission is this, in my opinion, which is a map of how total water storage, again, combined, so it's basically freshwater availability. All the snow, the surface water, the soil moisture, groundwater together has changed over the last 20 years. The reds are loose, this is a map of the trends. So the red is losing, the blue is gaining, and I'll just walk through some of the major trends. So ice sheets melting, we don't have a color bar in there. We put the color on there because it would drown out the rest of the scale. So, the glaciers are melting, right? So, we've got high latitude, a climate change signal of high latitude precipitation increase. We've got low latitude precipitation increase, so you see this sort of banding. When you look at these maps, as long as I have, you start to see a lot of things. Some real and some that just drive you crazy. Mid-latitude drying, look at that, that's huge, right? That's all been drying. One of the more recent things we've been seeing is the high latitude melting and drying. 5 years ago, if we looked at this map, it would be all blue up here, which is consistent with the IPCC models. Now we're seeing a lot more melting, permafrost melting, ice melting, and so those regions are melting and drying. So that's relatively new. The extremes of flooding showing up around the world. This is over the last last 20 years. So these are like major floods. And major droughts, including, this region that we're in here. Now, again, 5 years ago when we wrote a big paper, it was sort of bluish down here in Mexico and Central America. Now it's this big, like, sort of mega region. And the same is true for this region here. Europe was a little bit more blue five years ago. So things have gotten worse. And here's our groundwater. And these are the major aquifers. I'll show you an aquifer-specific map towards the end. And so, we wrote a paper in 2015 that showed that over half of the world's major aquifers are being rapidly depleted. It hasn't changed. The numbers have only gone down. Okay, so how do we get to groundwater? So I said that Grace gives us the change in all of this. Say we're looking at a basin, maybe this is the upper Rio Grande, and Grace tells us the change in all of this, the surface water, the soil moisture, and the groundwater. So Grace gives us this delta S land. If we know that is the sum of the snow, the surface water, soil moisture, groundwater, so we can rearrange and solve for groundwater, which we've done many times. It works pretty well. It's never going to be like as good as wells in the ground, but it does give us a great regional and global picture. It's great, of course, to combine them together. So Grace gives us that change. The total change, if we want to isolate the groundwater, we have to remove that signal, the snow, the surface water, the soil moisture. And we do that by various means, just depends on what data are available to us. If we have observations, we use observations. If things aren't measured, like soil moisture isn't measured that well, then we had to rely on models. We use other satellite data. If we're doing a paper in Iraq, we're not going to have any access to any data. And so we do a lot more using satellites. So it's really just a function of what's available to us. But we just wanted to show, we are hoping to do more and more of this by satellite. So the Grace Follow-On launched in 2018. ASO, Airborne Snow Observatory, for snow water equivalent is airborne, but is kind of a prototype for a satellite. The SWAT mission, surface water and ocean topography, will measure change in surface water storage. And the soil moisture mission, NASA SMAP, as well as the upcoming mission, the NISAR mission, which is the NASA India radar mission. EcoStress for evaporation. GPS is great. I mentioned before, some of the smaller satellite companies, Planet, Hydrosat, and OpenET has been a big help. So we try to use a bunch of stuff. Some of our previous studies in papers that really made me finally realize that people actually do care about water. They just not really care about, some model that you built, and they just don't really care about the incremental things, but they care a lot about when you start writing papers like this. That, okay, India's got the highest rated groundwater depletion in the world. California paper back in 2011 got a ton of attention. Middle East, and on and on. I and my colleagues have written a bunch of papers like that. When we were doing planning, someone asked if I would give an update on California. This is our paper from the Central Valley at the end of 2022. And so going from 2004 to 2022, see the snow, surface water, soil moisture here, wet periods or dry periods in the background, and the change in groundwater storage. Just this sort of, little bit of increase. Everyone always wants to know. This group knows that the little periods of recharge not make a big difference in the scheme of things where there's active groundwater depletion. And so this is what we've been seeing with the Grace data. As of 2022, the last couple of winters were a little wet, so there'll be like a little hump, but then, just keep going down. So and it's been doing that for a long time. And so this is the longer picture going back. This is the combination of the USGS data, model and observation, calibrated groundwater model, Central Valley model, and the Grace data tacked on the end here. So it's a long-term decline. So California, not getting any better. Arizona, also not getting any better. We wrote basically the same paper I'm going to show you some new results for. We wrote it 10 years ago. It really just pointed out, hey, there's a tremendous, again, this group knows, tremendous amount of groundwater depletion that's happening. We spend a lot of time thinking about Lake Powell, Lake Mead, but no one's ever really talking about the groundwater. And so this is just sort of trying to raise awareness about how much groundwater actually gets used. And so this is upper basin, lower basin. Not many people paid attention back then. Let's hope more people pay attention now. So upper basin, lower basin, changes in total water storage. So you can see the decline. I've got it here in kilometers cubed here. I should have done that in million acre feet. And in terms of groundwater, so we went through this exercise of subtracting the surface water, the soil moisture, and the groundwater. And so I have a time series over here, and the trend is about 1.4 million acre feet per year groundwater loss in the lower basin, and then mapped it out a little bit. And so you can see, so these are some of the active management areas here, shown with the light blue. There's a little bit, better, still being depleted, just not as badly in a couple of these active management areas, but some of these others are not doing so well. And just showing the percentage of the total water storage loss, how much is coming from groundwater. So a lower basin, 76% of the total water storage is coming from groundwater. Some of the work we're trying to do to enhance the resolution, sort of blend things together. So we've got the GRACE data, we've got ground-based observations, we've got all these satellites that I mentioned. And so we do want to be doing things at a high resolution. And so that we could scale up to whatever template we need. Maybe it's counties, maybe it's basins, maybe it's something else. And this is kind of where we're at right now. And this is, again, a blended product of 25-kilometer GRACE data, adding in a bunch of stuff that I just showed you to try to get down to 1 kilometer. This is a preliminary result, not even close to being ready for prime time. But happy to share with you that it's work in progress. Okay, so, what are we going to do? I don't know. I don't know the answer. I think that our goals are aligned. Everyone here is probably on the same page. I used to say that when I worked at NASA, that I was a rocket science, but the work that I was doing wasn't really rocket science. It was basically just accounting, right? But when you think about the bigger water picture, it actually is rocket science. It's so complicated because of the socioeconomics and the politics and the policy and the vested interest and the water rights, as well as the accounting and the public awareness. It's very complicated. This is an update to that global paper we did, showing that this is a huge problem. It's a global problem. Over half of the major aquifers, these are the ones that are recognized by the United Nations, are being depleted. Some papers we've written. Here's one I did with Grant Ferguson. Just want to give a shout out because he's the Darcy lecturer. He's coming to our various universities over the course of the next year. I don't know. I think we need to do a lot of jumping up and down and trying to get people's attention and then trying to drive action. This is the GRACE map just for the United States, and so we can see, here's the lower Ogallala, and you can see the Central Valley pop out there. We had some discussion in our planning meeting. Hey, what did it look like? Hey, what's the Rio Grande look like? Here it is. Some of these are at different scales, by the way, so it may be better to look at the colors. None of it's good. In these next few maps, go back here. It's the Southwest. In terms of the United States, it's the Southwest that's really in the roughest shape. So we can map this to any template. Here's the trends in lower Colorado and Rio Grande and California. This is a different scale. The California numbers are actually the worst. So the whole southwestern quadrant. Here's the major aquifers again. There's no way that I'm going to show you this that it looks good, is what I'm saying. And even this one, there's a lot of different ways we can get this information out there, and none of it's good. So what do we need to do about it? One of the things I do is communication. This is an opinion piece they wrote for the New York Times. If you actually read it, it actually has nothing to do with, of course you can imagine the amount of hate mail I got about this. And the comments had to be stopped after a couple of hours. It actually has nothing to do, the last thing I want to do is pump the Great Lakes. But we don't get to write our own headlines, especially with the New York Times. But, what are the things that I did say? Okay, well, I want to ask this question. What happens, so these are quotes, what happens to the nation's food production if groundwater actually runs out? Do we really have a plan? I was on the NASA Board of Agriculture and Natural Resources for 6 years. It wanted to do a study on groundwater security for food security. We could never get it funded. So we have no plan. If we want to sustain groundwater supplies for future generations, we'll need reliable estimates of what's available in key aquifers, how quality changes with depth, and how much can be safely pumped without risk of running dry. In other words, how much do we have? How much do we use? How's it changing over time? How are we going to fill that gap? How are we going to minimize that gap? What are we going to do to change the supply? What are we going to do to decrease the demand? And we have to prioritize. I'm big on the exploration question, not everybody is. We have to prioritize systematic exploration and evaluation of what's in the ground and make a plan to end or dramatically reduce groundwater depletion. I actually had end in here originally, but I put dramatically reduce because I don't think we can end it. And so we can maybe talk about that in our panel. And so, PCAST, I think, was really motivated, the President's Council of Advisors on Science and Technology, really motivated by all the coverage that was in the New York Times. I can't even remember, I guess it was maybe the coverage was in 2023. There was a lot of it. And so, yeah, it was in 2023. And so they did a study, and I made sure that how much do we have, how much are we using, and how is it changing over time, got in there, and it came up right on top. And so, which is awesome. And so, which is the nice way to close and say, right, so we need this whole of country comprehensive picture of storage, withdrawal, and recharge. How much groundwater, how fast it's being depleted, how, is it being replenished? More or less there. Now, given our change in administration, this may go nowhere, which is sad, but there is a pathway to get the message out, and we have all used it, and we have to keep on it. We have to keep doing the research. We do have to keep communicating about it. Some of us are involved in projects now, at least on a state-by-state level, that allow us to engage more directly with stakeholders, which is awesome. I was talking to Rosemary. Rosemary Knight works a lot in the state with stakeholders in California. I'm able to do now the same in Arizona through some funding that we have. And it's great. And so I'm at the point, I think, in my career where I'm very happy to have small wins. And I would love to save the world, but I'm happy to see Arizona's adding another active management area. I think that's great. We've got some new technologies. We're going to see some of them today. They can be real game changers. Let's make sure people know about them and use them, and make sure we do that engagement. So I'll stop here. Thank you.